So I want to talk about this framework called the dissipative negentropy allocation framework. It really is driven off of quantum foam, and I do want to talk about that a little bit. So let me give you a bit of an introduction here, just in plain English. So we have to talk about sol gel, like a solution to gel. I'm not sure if you're familiar with those colloidal systems. We need to discuss symmetry. We need to discuss sinks, like spectral sinks. When we talk about quantum foam, let's just start there. This is not any mystery. We're just saying that the world is full of these micro processes like fizzes and bubbles and poppings. These are just patterns that pop in and out constantly, and they don't persist. Now, most micro patterns, they don't persist, and most micro patterns are reversible. So we call that sol, or it's a solution, or it dissolves. Then some of these micro patterns do get stabilized by context, by constraints, by invariance in systems, and those are the rare bits that become gel. So again, a sol gel system. Why is there so much fizz in nature? It's simple because all of this small scale noise is very cheap, but any kind of stability becomes more expensive. So it's easy for fleeting micropatterns to appear and disappear. They don't demand long-term energy, they don't demand any structure. But making something last, that's the gel component of our process here, that actually takes work. You have to have a mold, which we call invariance. You have to have a reason, which we call goals, and you have to have a place to lock them in, and we call those sinks. And so the net effect of a sol gel with your invariance and your goals and your sinks, the net effect is that the micro is mostly sol, and the gel happens selectively only when it fits in with some kind of beneficial future counterfactual. So what we're doing then is we're borrowing from the future. Again, think quantum foam. But we have to talk about what that means and what that doesn't mean here literally, because it doesn't mean that time runs backwards. It doesn't mean that information travels backwards from the future. All it means is that we decide right now using forecasts that are refined as new data arrives. So what we're doing is we're letting likely future needs score today's tentative steps, and we use that as a smoothing mechanism. So think of it like this. If a draft looks like it will fit tomorrow's plans, we keep shaping the draft. But if not, then we keep it fluid. So the outcome of this is you end up with fewer regrets. You commit later and you commit smarter, and so you erase and you redo less, which just saves energy. We also want to talk about what evidence can we find concerning the jitters that actually matter. So tracks in the foam, so to say. So let's think about at 3 levels where you have these micro tracks. These are faint footprints of what was explored. They might be tiny biases, they might be correlations, they might be partial alignments. But then there's a mesolayer. We're going to call it micro tracks first, mesomemory second. And mesomemory turns the useful jitters into notes, into counters, into version marks. But these are all still easy to edit. We haven't made any commit yet. And then the third step is macro protocols, and these, they only adopt the patterns that repeatedly prove their worth. Those are the ones that become standards. Those are the ones that get committed at the spectral sinks. And so let's discuss why microstructures dissolve and why it's good that they do. Now, we talked about symmetries, we talked about invariance, and you see, because without any kind of a mold, a pattern, it costs more to maintain than it returns to the system. And so that's why it fades. That's why entropy wins. And what that does is it keeps the system light. The only patterns that persist are the ones that add value. The value-adding regularities survive. And what you do then is you just avoid clutter. You also avoid housekeeping heat by letting all those weak patterns stay sol. They stay solvent. And again, symmetry is the mold. So this is how the foam can gel effectively. And what symmetry means in this case is that the same move works in many places. So if a micro pattern fits a shared mold, it's cheaper to reinforce. Then also equivariance, it keeps procedures consistent when you shift context. And so you don't need a bunch of custom hacks all the time. And the result from that is that you have one template that has many uses, and that leads to less energy per commit. So we talked about the sinks, these spectral sinks, where the fizz becomes the form. Now, a sink is a design checkpoint that can absorb irreversibility well. Think of your final write instead of your rough draft. It's like a merge gate. It's like a sign off that, yes, this is where we want to make a decision and commit. So you keep the foam exploratory and you keep that upstream, and then you commit downstream at the sink when confidence is high. And what that does then is it clusters the heat of change in safe zones, and it keeps everything else flexible. We also have to talk about fractal alignment. So if we're using the same decision templates and they repeat across different levels, like from sense to seed to commit to align to reinforce, then you could actually think of this in a practical sense, that you might have microsensors, and then they resolve to personal habits, which resolve to team protocols, and the whole system it all rhymes together. So what you're doing in this fractal alignment is we learn once and we apply many times. What that means is that the foam actually feels less chaotic because your molds match across all the scales. So you have invariants at the macro level, like we talked about macro protocols, and those invariants at the macro level, they actually map persistently to the mesomemory level, which maps persistently to the microtracks. So you have fractal alignment. And out of that emerges some time-respecting planning. You have a clear arrow of time. You end up with much better timing. And when you're filtering, you're adjusting your prior beliefs to what just happened. So, think Bayes. When you're smoothing, what you're doing is you're just asking which near future outcomes you care about, and then you score today's opinions by how well those would fit if certain futures occurred. And then you still act in the now, however, you still act in the present. And what you gain from this process is timing. You avoid locking into any links that you have to break later. Then we also have to talk about thermodynamics and the common sense of energy conservation. Why does this save energy? First of all, irreversibility is expensive, because if you need to erase or if you need to revise a record, that is always going to have a minimum energy price. So if you delay your commits until your smooth confidence is high, then you're going to erase less. So, and also, don't forget symmetry, because if you enforce a symmetry, you sustain order with less control effort, and that is critically important. The ability to predict future counterfactual, and the ability to enforce symmetry and structure, to detect and enforce structure, that is a key to energy efficiency in cyber intelligence. Now, what we're trying to do is we're trying to convert from foam to form gently, like in a controlled way. So we draft the ideas lightly, we test them against tomorrow's needs, and then we publish only at checkpoints. And then we prototype our software, we run integration tests, and we only merge at these compression gates. Then regarding data, we want to keep our data raw and fluid, but we only want to certify when we're ready to publish a catalog. And everywhere we go, whether it's molds and standards, whether it's sinks and gates, whether it's delayed commits for fewer rewrites, we're using the same mathematical and physics-based strategies. Now, we want to make sure that we also qualify what we're not doing. I mean, we're not saying that the future causes the present here. What we are saying is it's present time decision making informed by forecasts. And we're not using speculative physics. Foam in this context is a metaphor for high frequency fluctuations plus selective stabilization. Now, that said, we've built this solidly on the mathematics of quantum classical hybrid. So there is application for this, maybe near future application in quantum computing. But what we're saying right now is that we can use this on bitwise CPU computation, right? And that's what we're running here. I'm not even running a GPU on this script. And we're not saying that this is some kind of unbounded or some infinite state space. We're just saying everything is finite, everything is computable, everything is measurable. When we have fewer regretted commits, when we have more reuse, and when we have localized irreversibility, we get hyper efficiency when it comes to both energy and information parsimony. So quantum foam then, in this lens, quantum foam is just the ever-present fizz of tiny options. And agency is the craft that sifts the fizz through some kind of shared molds, these system invariants, and it also waits until the pattern is clearly useful. And then it gels at the right sync. That's your commits. That's how you turn micro restlessness into durable structure with minimum waste. And you're just dealing it with one well-timed commit at a time, right? I'm trying to describe to you the framework before we jump into the code here a little bit. So with that said, I just want to talk a little bit about what this DNA framework is. It's in this DNA engine. It stands for dissipative negentropy allocation, and that's just a mathematical computational system. It's designed to understand and to optimize how quantum and classical systems dissipate energy and how they manage information. And at the core of it, it just addresses a fundamental question. When a system must lose energy or information to accomplish some goal, where should that loss occur, and how can it be structured to be the most efficient as possible? That's the question we're asking and answering in this framework. So imagine, for example, that you're building a manufacturing facility and you need to move materials through different stages, and eventually you have to throw away your waste product, right? So this dissipative negentropy allocation framework, it helps to decide which stages are reversible. Those are the ones that you could theoretically undo, compared to which stages are committed or irreversible operations. That's where you have points of no return, and you have to make commitments. The framework also prices the cost of information erasure using thermodynamic principles, and specifically, of course, the Landauer bound. The Landauer bound states that erasing one bit of information requires at least a certain, although albeit very small, amount of energy. And so we're going to look at the code here, and this abstract mathematical framework is implemented as a simulation engine that combines the quantum mechanics and the classical information theory. And the simulation, it tracks a hybrid classical quantum system where quantum states evolve according to thermodynamic rates, according to classical information states that get updated through observations, and the whole system is being analyzed so that we can measure the entropy production, the information preservation, and the optimization metrics. And so at the very top of the code here, we have a couple of global numerics. This global constant here, this EPS floor, actually let me bump up the size of this a little bit. We can see those. This EPS floor right here, this is set to 1 times 10 to the negative 12th, which represents a numerical floor. That's a minimum positive number. And we need it for avoiding mathematical singularities, because many calculations are going to involve logarithms and divisions, and those are going to break catastrophically, actually, if you feed them exact zeros, right? So the EPS floor, it just makes sure that whenever the code needs to compute a logarithm of a probability or maybe an eigenvalue, that the number is guaranteed to be at least e times 10 to the negative 12, a positive number, small positive number, and that's going to prevent any infinities. It's going to prevent any not a number errors, NaN errors. Now we have another global constant here, the h bar, and we've just set that to 1. This is Planck's reduced constant, fundamental for quantum mechanics, really. And then just by setting it to dimensionless 1 in the code, then the simulation adopts a constant unit system where quantum effects are implicit rather than explicitly scaled. And this is a common, everybody does this in computational physics just to simplify the numeric work. Okay, so that's some global numerics. Now we have a couple of data classes here. Here's the main controls data class. And this is the first user-facing class, right? It's just defining a data class, a lightweight container for related configuration values. And this object holds all the parameters describing the quantum and the thermal environment. So we have this omega parameter here, and it represents a coherent coupling strength measured in energy units. So specifically, it controls how strongly the quantum 2-level subsystem, like the excited state of an atom, for example, how that subsystem can be coherently driven. When omega is large, quantum superpositions and Rabi oscillations, they occur rapidly. But let's go to this next field, delta E. This is the energy difference between the ground state and the excited state of the quantum system. And together, these two parameters, they define the quantum block Hamiltonian. That's the operator that describes the quantum system's time-independent energy structure. Now, and then you have this K-sync base and the K-sync on factor. These control how quickly the system can transition into a sync state, which is that final committed state from which there is no return. So think of it like an irreversible process, like erasure or like commitment. The K-sync base is measured in units of inverse seconds. That's like 1 over s. That's a rate. And it sets the baseline rate. And then the K-sync on factor, that's a multiplier, such that when the classical state is condition 1, that's a specific classical configuration, then the sync rate is multiplied by this factor, which allows the sync rate to be context dependent. Okay, now you have the temperature and the KB parameters. They're just specifying the physical temperature in Kelvin and the Boltzmann constants in joules per Kelvin. And they both together, they allow the code to compute thermodynamic quantities, for example, thermal energy scale, KBT, which is pivotal in equilibrium statistical mechanics. At low temperatures, the thermal energy scale, obviously, that'll be small, making the quantum effects dominate, but at high temperatures, the thermal noise is going to dominate. Then you also have this symmetry penalty weight, and that's a numerical weight that would penalize symmetries in the system if they're non-zero. But in this particular run, we just set it to 0, meaning that the symmetries are not being explicitly enforced. And then you have the energy units here, finally. And now this is a string flag, and it tells the code how to interpret the energy parameters. So if the string is kBt, then omega and delta E are assumed to be specified in units of thermal energy. So kB times T. But if the flag is J, or joules, then it's interpreted as absolute energies. And this is just a flexibility option that allows the code to adapt to different experimental contexts. So I just added that in there to make it flexible, although we're using kBt here, obviously. Now we have this next data class. It's a small one, classical rates. And these constants, k on and k off, okay, they represent the rates at which a classical system transitions between two states. So for example, think of a regulatory switch in a cell that might flip on at a rate k on, or 1 over s, right? And it might flip off at rate k off 1 over s. So these rates define a continuous time Markov chain, the classical analog of quantum evolution. And together with the classical state probabilities, these two rates, they'll determine how the classical information state, a probability distribution over two classical states, they determine how that evolves deterministically over time. Now you also have the, the emissions model right here. This is capturing the observation process. The system can't be observed perfectly, right? Observations are always noisy, and so this data class holds these two conditional probabilities, the py1 given x1, and that's the probability of observing a 1 when the true classical state is 1, and then there's py1 given x0, which is the probability of observing 1 when the true classical state is a 0. And in the default configuration, we're using 0.9 and 0.1 respectively, and that just means that the observation is going to be fairly reliable, but it's going to be imperfect. And we're just creating a filtering problem, because given a sequence of imperfect observations, the system has to still infer the true classical state, which introduces posterior uncertainty, and thus it introduces entropy. Yeah, we've set those at just imperfect values. Okay, we're getting into the bridge config data class here, and it encapsulates all the parameters related to the bridge subproblem, and that's the entropic optimal transport calculation. So a bridge here, it's a reversible or near reversible process that transports the system from one state to another while minimizing its dissipation. So the bridge DT factor, this is an important multiplier. The simulation runs with the time step dt is equal to 0.01 seconds, and so the bridge calculation operates over a longer effective time horizon of dt times the bridge dt factor, and Setting this to 5 means that the bridge calculation is looking ahead by 0.05 seconds, which is a longer window than the single simulation step, right? And so the multi-step look ahead, that's going to allow the bridge to find smoother and more optimal transitions. Now you have this H bridge steps. That's a parameter which we've set here to 3, and this further extends the planning horizon. So instead of computing optimal transport over a single DT sized step, the algorithm plans over H bridge steps, classical state transitions. So this multi-step approach, it can find better solutions because it's seeing further ahead. Then the kernel bias parameter, that introduces a small asymmetry to the baseline classical transition kernel. And by default, the classical Markov chain is reversible. That satisfies detailed balance under the stationary distribution. However, if this is the case, then finding a unique optimal bridge can be ambiguous, right? Many different paths might achieve the same theoretical minimal cost. So the kernel bias set to 5 times 10 to the negative fourth, a really tiny number, that just breaks the symmetry slightly, which it's going to help the solver to converge to a unique solution. Now we also have the OT-reg epsilon parameter, and that's the entropic regularization strength for the Schrödinger bridge solver. In entropic optimal transport, a small regularization term is added to the objective, and that's so that we can ensure strong convexivity and numerical stability. And this 1 times 10 to the negative nats, this is a moderate regularization that balances between following the true optimal transport geometry and at the same time maintaining numerical stability. Then finally this OT max iter, it sets the maximum number of iterations that the solver will attempt at 5,000, and the OT tol, that sets the convergence tolerance at e times 10 to the negative 12, defining how close to perfect the constant satisfaction has to be before the solver declares convergence. And then down here you've got your DNA configuration here. The main configuration class, it's tying together all of the operational parameters for the simulation. So this DT parameter, again, this is just the simulation time step in seconds. We already said it's 0.01 seconds in the default run. And then at every DT seconds, the system advances 1 discrete step. That's all that means. And then the TN parameter, that's the total simulation duration, which is that 5 seconds. So with DT set to 0.10, there's going to be approximately 500 time steps in the simulation. And then we have this tau pred parameter that's 0.05 or 0.5 seconds, and that defines a prediction horizon that's used for mutual information calculations. So when the code estimates how much the classical state can be predicted from the past, it's looking back over a window size of tau pred. This is used to compute the accessible negentropy. That's just the amount of the useful information that's in the system at any given time. Then you have this n trials parameter, and that's a historical artifact. It's kept for API compatibility. We're not using it here, but it would be the number of trials in a Monte Carlo estimate, for example. Now you have this epsilon entropy parameter set to e times 10 to the negative 10th. It's a floor for the logarithms and the eigenvalue operations, and specifically in the entropy computations. And it's much smaller than the EPS floor, but it serves basically the same purpose of just preventing any singularities from converging. So when computing the von Neumann entropy of a quantum state, that's the quantum analog of Shannon entropy, the eigenvalues smaller than epsilon entropy are floored to present the logarithm blowup, right? Now we have a seed parameter, which is obviously, it just sets the random number generator seed so that we have reproducibility, meaning that every time this simulation runs with seed like 1, 2, 3, it's going to produce identical results because the pseudo-random number sequence is set to be deterministic by this seed. We have a use smoothing flag. That's a Boolean, and it introduces whether to apply smoothing algorithms to posterior estimates. And this is related to the mathematical technique of Rausch-Tung-Streibel, or RTS smoothing. And RTS smoothing can improve posterior estimates by considering both past and future observations. And in the current code that we just set this to true, but we're not really actively using it in the loop. And then finally we have the symmetry template norm and the bridge CFG. Symmetry template norm is another parameter related to enforcing symmetries. In the default run, it's set to 0, meaning we're not really enforcing any symmetries here in this run. And then you have the bridge CFG. That's an instance of the bridge config, bundling all of the bridge related parameters into one variable here. Okay, so we've covered all the data class setups, and we now want to just start taking a look at these utility functions. And we've defined several of them here. They're basically just handling operations safely. So this safe log Herm method here, inside here we're computing the matrix logarithm of the Hermitian quantum state, because in quantum mechanics a Hermitian matrix that's one that equals its own conjugate transpose. So computing the logarithm of a density matrix, that's necessary for entropy calculations. We have to do that. And the function works by diagonalizing the input. That means breaking it down into eigenvectors and eigenvalues, and then we take the logarithm of each eigenvalue and we reconstruct the matrix. And again, importantly, it floors the eigenvalues using that EPS parameter before you take the logarithms, so you don't get any logarithm singularities in the computation. And that's really essential for stable computation of the von Neumann entropy. Then you have this predict PSD trace 1 function, which ensures that a quantum state is both positive semi-definite and also that it has trace 1. And after numeric operations, the quantum states, they can become slightly corrupted, and they might develop negative eigenvalues from rounding errors, or their trace might drift from 1. And so this function heals those problems by diagonalizing, by flooring negative eigenvalues to 0, or the floor EPS, and then renormalizing the trace back to 1 again. And this is a key safeguard. It simply ensures that all the quantum objects, they remain valid density matrices throughout the entire simulation. Okay. And then of course this is we're just defining our plot aesthetics here in this function. It's not really that important. So where are we now? We're actually going to scroll down here to the DNA, where's it, DNA engine class, and talk about this for a minute. This is the main computational engine, and its constructor here, it receives these 4 configuration objects: controls, classical rates, emissions, CFG. The first action is to seed the random number generator with the cfg.seed, which ensures the reproducibility, and then the constructor calls this build spaces and ops function, which constructs the quantum mechanical operators and the spaces needed for the simulation. So we can scroll down here and look at this build spaces and ops function, which is called in the init method. The code here first establishes the dimensionality. Okay, so the quantum state for each classical subsystem, there's one for each classical state, the value 0 or 1. The quantum state lives in a 3-dimensional Hilbert space. These 3 dimensions, they correspond to the ground state G, which is index 0, and you'll see those being defined here. Ground, and then this is excited, and then this is sync. And you can see here that the excited state is a 0 with an index of 1, and the sync state is S with an index of 2. And of course the sync state is the one that once you enter it, you can't exit. That's the commit state. And the dim block is set to 3. Now, the total quantum system contains 2 of these blocks, 1 block for each classical state. So the total Hilbert space dimension is dim total set equal to 2 times 3, or 6, right? That's the total dimensions. Now in the QTIP, you'll notice we're using QTIP up here, and you can see it in the includes, right? We're importing QTIP. In QTIP, in QTIP, a quantum system is always represented by QObj, or a quantum object. And working with a 6-dimensional Hilbert space means that density matrices are 6 by 6 complex matrices. And the code creates projection operators, PG, PE, and PS. And these project onto the ground, onto the excited, and onto the sync subspaces respectively. And we use these throughout the whole framework in order to measure populations. Now, still in the same function, we have to set up the Hamiltonian, the quantum Hamiltonian, the energy operator. And the energy splitting between ground and excited states is this delta E. We're scaling it to joules via this energy scales method. And then the coherent coupling strength is omega, and we're also scaling that. And so the Hamiltonian consists of energy cost for the excited state, coherent tunneling between the ground and excited states, and of course that's with strength of omega. And then the sync state is inert, so zero energy and no coupling. And then Hamiltonian generates the unitary evolution, right? Reversible energy conserving dynamics. Of course, then we have to set up the Lindblad operators. And so this is beyond unitary evolution, right? The quantum systems, they dissipate and they decohere through environmental coupling. And these are modeled using this Lindblad jump operators. So the code sets up three different types. First of all, you have LGE down block. That represents downward transitions from an excited to the ground state. Of course, spontaneous emissions there. And they're modeled with the rate gamma down. Then secondly, you have LGE up block, which represents upward transitions from ground to excited state, so thermal absorption, and that's modeled with gamma up. And then finally you have the third one, the sync L block, which represents transitions from the excited to the sync state. That's the committed irreversible erasure process again, and the rate of that is K-sync. Okay, now since there are two interdependent quantum blocks, one for each classical state, the code has to create embedding helpers. And the operators constructed above, those are for a single block, but the total system is a tensor product of two blocks. So the function embed block op, that's right here, it takes a block local operator and it embeds it into the full space, either by placing it in the left block and zeroing the right, or placing it in the right block and zeroing the left. Anyway, this allows the full system to be a block diagonal structure where each classical state has its own independent quantum evolution. And we also have to construct the Gibbs reference state, because for thermodynamic calculations the code needs a reference state, the equilibrium Gibbs state at a given temperature. And that state represents what the quantum block would equilibrate to if it was left alone for infinite time at temperature T. And so to ensure numerical stability, the Hamiltonian is shifted by its minimum eigenvalue, E min, preventing any extremely large or extremely small exponents. And the resulting state, which is rho eq block, that's the Gibbs reference, and it's stored for later use. It's right down here. And this reference is crucial for computing entropy production, and entropy production is always measured relative to a reference state, of course, defined here. Let's actually talk about the classic generator. It constructs a rate matrix for the classical two-state Markov chain, and that's a 2x2 matrix where the A 0, 1 it equals K off. That's a translation rate from state 1 to state 0, and A 1, 0 equals K on, and that's a transition rate from state 0 to state 1 with diagonal entries set to maintain row sums of 0. It's a generator of a continuous time Markov chain. And then this next one, step classical, it advances the classical state probabilities by one time step, and it uses the matrix exponential of the rate matrix times the step size, dt. And this is the closed form solution to the Kolmogorov forward equation, so that after exponentiation the result is renormalized to ensure probabilities sum to 1. So you're handling any rounding errors by doing that. Okay, thermal rate calculation. This function computes the spontaneous emission of and simulated absorption rates based on temperature and energy splitting, and it uses detailed balance. The ratio of upward to downward transition rates is determined by the Boltzmann factor, and at low temperature transitions favor the ground state, but at high temperature the rates become more balanced. And this ensures that the system approaches the correct Gibbs equilibrium. And then the function rates for block, here it's just returning 3 key rates for a quantum block given a classical state. The sync rate is enhanced by this K-sync on factor when the classical state is 1, allowing context-dependent commitment, and the thermal rates are computed and returned together. So we're returning these together. Now, building the total systems operation, we've got this total ops for rates. This constructs the full Hamiltonian and the Lindblad operator lists for the total 2-block system. It embeds the single block Hamiltonian into both the left and right blocks, creating an additive total Hamiltonian. And then for each classical state, left and right blocks, it assembles the Lindblad operators with their rates, creating a single list of tuples. You have a tag, you have operator, you have rate, and they describe all the dissipative channels. Now this GKSL evolution, here you've got this function Lindblad generator. Where is it? Yeah, this Lindblad generator function. There is some math in here. We call it GKSL. This is Guarini, Kasakowski, Sandharshan, Lindblad, the GKLS equation, and it's just a quantum version of the Kolmogorov equation. And what it's doing is it's computing how a density matrix evolves under combined unitary and dissipative forces. So the sum of the dissipation terms represents irreversible dissipation. And then this function, steady state block, it finds the steady state density matrix for a single quantum block under given rates. So if the Hamiltonian and the Lindblad operators are time independent, then the system eventually reaches a fixed point where the time derivatives vanish. Now, the QTIP library, it just gives us a steady state function that solves this eigenproblem. If the convergence fails, the code falls back to time evolving the system for a long time and then extracting the final state. And then this function, rho SS total, this constructs the full two-block steady state by combining individual steady states weighted by the classical state probabilities. And that represents what the full system would reach if you just left it undisturbed. Now, down here you have this spawn rate. You've got this compute spawn rate function. And this calculates the total entropy production rate. The SON formula measures entropy production as a quadratic form involving the difference between the current state's logarithm and the steady state's logarithm, with the GKSL generator applied to it. So now intuitively you can just think of this as measuring how far the system is from equilibrium. The larger the difference, the faster the entropy is being generated, and the rate is always non-negative by thermodynamic laws. Now we also have this compute channel entropy rate. Here, we're computing the entropy production attributed to a specific channel, and we're identifying it by its tag, like sync. And then, by filtering the Lindblad sum to only the sync channel, the code measures how much of the total entropy production comes from irreversible commitments versus other dissipation. So this decomposition is central to the DNA frameworks, separating SOL, reversible bridging process, from the GEL, irreversible commit process. So we need to know the difference, and that this function handles that. Now, we also have a function down here, compute jump intensity fraction, that method. And it's measuring how much of the total quantum jump intensity is concentrated in the sync transitions. The jump intensity for an operator is the expected strength of that jump in the current state. So by comparing the sync jump intensity to the total, the code gets a measure of the GEL localization, meaning whether the irreversible process is indeed concentrated in the sync channel as it was intended to be. Okay, we have the init state function right down here, and that sets up the initial quantum state. Both blocks start in their ground state, G, weighted by the classical state probabilities, and this represents a prepared state at the start of the simulation. And then you have this baseline bridge kernel down here, which constructs a classical transition matrix that serves as a reference for the Schrödinger bridge calculation. And it exponentiates the classical generator over the effective time horizon at dt effective. Then it adds a small bias to break degeneracy. And that bias, it ensures the matrix is not exactly symmetric, because that would make the optimal transport solution non-unique, wouldn't it? So we have to have that not perfectly symmetric. Okay, we have the main simulation loop here. Now this simulate loop, and it's the core computational loop. It runs for n time steps, where n is equal to t end over dt, so that at each step there are several parallel processes that are occurring. First of all, there's the classical state that has to be sampled probabilistically from the filtered posterior distribution. Then an observation is generated from that classical state using the noisy emission model, and these observed values are recorded in the x trajectory and the y trajectory for later analysis. So you'll see them here. And then in the classical state belief is updated using Bayesian filtering. And the predictive step advances the probability distribution using that classical generator. And then the likelihood of the observation under each classical state multiplies the prediction. And finally, normalization produces the posterior. This is the standard recursive Bayesian filter and the optimally efficient way to estimate the true classical state from noisy observations. And then after the classical update, the quantum state evolves according to the GKSL equation over time step dt, and the QTIP library's mesolve function integrates the equation. Mesolve is down here. It integrates the equation and then it returns the involved state. And then once the quantum state is updated, you've got several diagnostics that have to be computed. You have the total entropy production rate. That's computed using that Swan formula. Then the sync-specific entropy production rate has to be extracted. And the ratio, lambda sync, right here you'll find that. This ratio measures what fraction of total energy production occurs in the sync channel. Then the gel localization fidelity via the jump intensity has to be computed, and the posterior entropy is calculated from the classical state probabilities. And all of those quantities, they all have to be recorded in time series for later analysis. Now, the critical novelty in this DNA framework, it appears in the bridge residual calculation. The code calls the two-state bridge log synchron. We actually didn't discuss this, I think, but it calls it in that function. It solves a classical entropic optimal transport problem. So given the classical state at the current time and the previous time, that function finds the most efficient minimum entry production way, the most efficient way to transition between them. And so the maximum entry production, this sigma sol min, it's achieved by this optimal process. The minimum entry production achieved by this optimal process, that's the sigma sol min, that's subtracted from the actual entropy production sigma sol, and that's the off-sync component. And the difference then is the residual, the RSOL, and this measures efficiency in the sol bridging part. And if RSOL is 0, then the bridge is optimal. If it's positive, then there's room to improve it, right? That residual, it forms the basis of the DNA master inequality. It's a certificate that the actual entropy production exceeds the theoretical minimum by exactly the residual amount. And then finally, the loop, it computes the accessible negentropy down here, and that's the mutual information between the classical state at time t and the time t plus rho. And so this measures predictability, and it's related to how much information can be extracted from the system. Okay, so we have to go back to this two-state bridge log synchron, which is up here. And this is a sophisticated optimization algorithm that computes the Schrödinger bridge. That's the optimal entropy minimizing transport between two classical probability distributions. So here's the problem. I mean, given an initial distribution P0, and a final distribution P1, and a reference transition, which is PO, find a new transition matrix Q that transports PO to P1 while staying as close as possible in KL divergence to P0, subject to the natural constraint that Q has to be a stochastic matrix, meaning the rows have to sum to 1. Now the solver uses an iterative log domain approach, and so instead of working with positive numbers directly, because those can overflow or underflow, the algorithm works in log space, and that's numerically more stable for extreme values. So it parameterizes the solution Q equal to diag U K diag of V, where U and V are diagonal scaling matrices and K is a tempered version of the baseline kernel P0. By tempered, we mean it mixes in some uniform matrix to avoid the degeneracies. The algorithm iterates between updating U, that's the left scaling, to enforce row stochasticity, and updating V, the right scaling, to enforce the transport constraint. And each update is derived by optimizing the corresponding constraint in log space. The iteration is damped and normalized to prevent divergence, and as the iteration progresses, the diagnostics flow and rows, they measure how much the constraints are violated. And the potential consistency metric measures the discrepancy between two different ways of computing the optimal scaling, with another indicator of convergence. And then once converged, the function returns the minimal KL divergence achieved, the optimal matrix Q, and the diagnostic information about the solution quality. Okay, so let's go back down to this negentropy computation down at the bottom, and we're getting close to our completing our conversation here, but where is that? Yeah, the accessible negentropy series. What this does is it computes phi joule time series, which represents accessible negentropy. So loosely, that's the useful information in the system that could theoretically be harnessed. And for each time point, the code estimates the mutual information between the classical state at time t and time t plus rho using a sliding window. So mutual information, it measures how much knowing the past state reduces uncertainty about the future. And that is scaled by the Landauer factor to convert from information bits to energy, which is joules, and the result is phi joules of t, which has dimensions of power. Okay, now we have to talk about the main execution that's at the bottom of the script, and basically we can just talk this through. The framework is instantiated with concrete parameters, and it's executed. Then the engine runs a simulation. It collects 500 time steps of data, and then the diagnostic outputs at the bottom show the summary statistics. Like, let me go down here. Mean entropy, it shows production rates, it shows gel localization metrics, bridge residual statistics, and also the cumulative slack in the DNA master inequality. And the fact that the slack here is 0, we're showing here in the output, that indicates that the DNA MB inequality is satisfied at all times. Entropy production and energy dissipation are consistent with the theoretical bounds in this run. And the bridge dual gap proxy of approximately 0.014, this is indicating that the Schrödinger bridge solver converged to within a small tolerance of the optimal solution as well. So in summary here, the DNA engine combines quantum mechanics, classical filtering, thermodynamics, and optimal transport so that we can create this integrated framework which can track and measure and optimize the dissipation and the information processing in a hybrid classical quantum system. Each parameter, each function, and each loop iteration contributes to the comprehensive picture as we've defined it here.